Hi everyone, thanks for tuning into my talk. My name is Mia Weaver and I'm a graduate student at the University of Wisconsin-Madison. Today I'm going to be introducing my paper, Monitoring Latency on Submarine Cables, Limitations and Opportunities. In this work, we develop a capability for monitoring packet latency on submarine cables using active measurement nodes. This work is done in collaboration with my advisor, Paul Barford, and colleagues at University of Technology, Sydney and Northwestern University. I'll start with a quick overview of the Submarine Cable Network, or the SCN. The SCN consists of over 500 submarine cable systems and carries more than 95% of international traffic. These cables run along the ocean floor and surface at landing points, though they typically connect to Layer 3 infrastructure at further inland POPs. With growing demand from cloud services and AI, major tech companies are investing heavily in expanding this infrastructure. As submarine infrastructure becomes increasingly central to cloud and AI ecosystems, understanding its behavior is critical. Measuring the SCN reveals how links respond to load, environmental factors, and operational conditions, informing better network design and management. In this work, we use traceroute measurements of packet RTT to estimate minimum round-trip time, or min-RTT. Min-RTT reflects the physical baseline of a path and is insensitive to traffic conditions, so changes in this baseline indicate changes in the underlying infrastructure rather than congestion. In this work, we address the question of what it would take to develop a cost-effective capability for monitoring packet dynamics in the submarine cable network. Achieving such capability poses several challenges. Submarine cable ownership is distributed and largely private, making large-scale passive measurement infeasible. We therefore must rely on active probing platforms like RIPE Atlas, which introduce their own issues. For example, identifying vantage points that actually cross the target submarine infrastructure and extracting meaningful information from these inherently noisy active probe datasets. Traceroute-based identification is also difficult because cable systems share AS operators and landing point locations. We call the consecutive hop pair crossing the ocean the submarine link, but matching that link to the underlying physical infrastructure is complicated by operational overlap, routing fluctuations, and hidden Layer 2 infrastructure that might add a terrestrial component to the submarine link. In the following slides, I will discuss how we address these challenges inherent to active measurements and develop a methodology for vantage point selection and minimum RTT estimation in the submarine cable network, which raises the current state of the art. To address these challenges, we begin with the infrastructure itself. The first step is constructing a detailed view of the cable systems we aim to monitor. We built a detailed database of around 350 cable systems from public maps and operator documentation. This knowledge base supports vantage point selection, trace route collection, and infrastructure identification. All data used in this study, including the vantage points we identified and the submarine link IP addresses we identified, will be made publicly available. We select measurement vantage points under the assumption that nodes that are topologically and geographically close to a target submarine link offer the clearest view of its behavior, wherein noise from upstream congestion is minimized. By topological closeness, I mean that the distance between the origin and the submarine link is minimized in terms of network hops. By geographic closeness, I mean that this same distance is minimized in terms of RTT. Because traceroute probes appear to enter submarine infrastructure at ingress points which coincide with further inland POPs that then connect to the actual landing point via hidden Layer 2 infrastructure, we prioritize proximity to a coastal POP over proximity to the landing point itself. Using detailed knowledge of the target link, we search the full set of RIPE Atlas anchors for vantage points that meet two criteria. 1. They're operated by entities that use or peer with the submarine link's operators, and 2. They're near a coastal POP where the target submarine link operators are present. Once a candidate is found, we examine trace routes from the candidate to an anchor on the far side of the link. If we observe a hop pair matching the link's operators and locations, we include that vantage point in our study. We call the anchor pair used for gathering these measurements an origin and the target a destination, creating an OD pair. This figure shows the anatomy of such a measurement setup. The red solid line shows the underwater portion of the link. The dashed black lines represent lower layer infrastructure, which is invisible to traceroute measurements. The egress is simply the second hop of the link, typically located also at a coastal POP. In total, we analyze samples from 101 submarine links, connecting all major regions of the world and spanning 32 ASs. We identified, on average, 7.85 right batless vantage points for monitoring each submarine link included in our study. Now, let's dive into the development of our minimum RTT estimation techniques, starting with a brief overview of fundamentals. Under stable routing and fixed probe sizes, an RTT can be viewed as a fixed minimum delay R plus some congestion term Q. We denote RTTs to the ingress of the submarine link as R1, and RTTs to the egress of a submarine link as R2. Each traceroute provides up to 3 samples of R1 and R2, and these R1 and R2 series form the basis of our minimum RTT estimators. Extracting the submarine link's minimum delay from R1 and R2 requires that reverse paths from the ingress and egress paths share the same route, save for, of course, the additional hop from the egress to the ingress. And we'll refer to ingress and egress as I and E respectively. This is an assumption we called maximally shared paths, or MSP. When MSP holds, we can estimate the submarine link's minimum RTT by simply subtracting the minimum of R1 from the minimum of R2. We refer to this as the unpaired estimator, and this is illustrated in the figure on the right. MSP is, however, an unsafe assumption. This is because it is possible for the reverse path from the egress point E to take a different path through the network. When this happens, the reverse path pollutes the minimum RTT estimate calculated by our unpaired estimator. The plot on the right shows how the unpaired estimator generates an erroneous estimate during MSP failure. Examining level shifts in the R1 and R2 time series provides one of the clearest indicators of MSP failure in a dataset. Level shifts result from changes in underlying infrastructure and are endemic in the internet. The plot here provides an example where 2 level shifts are seen in R1, the orange signal, and 3 are seen in R2, the green signal. The earliest and latest level shifts match exactly, revealing that those changes occur on shared portions of the path from the origin to the ingress and the origin to the egress, and so they cancel out in the delta R time series. The delta R time series is constructed by subtracting R1 values from their paired R2 values and is meant to encapsulate the RTT over the submarine link. The remaining level shift is in R2 only. Such an unshared level shift induces a level shift in delta R. This is nominally impossible for a submarine link. There can be no change in the underlying infrastructure of the actual cable. This shows that MSP does not hold for the trace overall. One of the limitations of this unpaired estimator is that it is not level shift aware. It sees only the lowest level in a multi-level dataset, which results in either unused samples at best or completely erroneous estimates at worst. I'll now describe our approach to replacing this unpaired estimator with a more robust method that mitigates noise from MSP failure. We first pre-process the data using 2 filters to reduce bidirectional congestion noise and expose clean level shifts. First, we apply minimum filtering to each traceroute trio, yielding new estimates P1 and P2, where P1 is the minimum of an R1 trio and P2 is the minimum of an R2 trio in a single traceroute. This yields values that are pulled closer to the true minimum of their respective paths. Then we apply a sliding median filter to the sequence P2 minus P1, thus yielding a latency signal delta P, where shared level shifts cancel and unshared level shifts are preserved. We refer to each level shift region as a zone L. This process transforms the noisy raw signals in the upper plot into the cleaner, more symmetric P view that you see in the lower plot, where the delta P signal retains the amplitude and location of the unshared level shift. We then estimate the minimum RTT of each level as the median of delta P within that zone. We use the median as we expect noise to be relatively symmetric around the true minimum, thus indicating that the median is a closer approximation of the minimum. This gives us a minimum estimator that is robust against artificial dips or spikes in the data due to upstream congestion. Building on this, we now develop a robust estimator that draws on the entire ensemble of origin-destination pairs crossing the link. After examining ground truth examples, we found no reliable predictor for identifying the preferred level in a latency signal, In other words, the level corresponding to MSP success. Geographic and topological proximity may aid in reducing traffic from upstream congestion, but they do not guarantee that an OD pair will obey MSP. Additionally, simply choosing the lowest level does not indicate that MSP holds either. In fact, even in the case of submarine links with no level shifts, OD pairs capture distinct latency profiles, and we have no mechanism to confirm which time series best reflects the true minimum RTT. Given this uncertainty, we adopt a neutral strategy and average the minimum RTT estimates across all levels and all OD pairs monitoring a given submarine link. This ensemble averaging yields a conservative and robust estimate, avoiding overcommitment to any single path and mitigating the risk of bias introduced by unrecognized MSP violations. So, in summary, our unpaired estimator averages minimum RTT estimates over each OD pair, whereas our paired estimator averages minimum RTT estimates over each OD pair and level that we see from an OD pair signal. Having developed both estimators, we evaluated their accuracy using 6 ground truth datasets. I'll now show you how they performed. The figure on the left reports estimator accuracy as a percentage relative to a respective ground truth dataset and illustrates the strong performance of both the unpaired and paired estimators. We also included a naive minimum RTT estimator, which simply uses the minimum differential between a paired R1 and R2. Across all submarine links, the unpaired and paired estimators produce values within 9.5% of ground truth, representing improvements over the naive estimator ranging from 40% to 88%. Since the performance of the naive estimator is so poor, we drop any further comparisons with it. In the center plot, we see the average absolute error, computed as the mean absolute difference between the ground truth minimum and the estimator output. For the unpaired estimator, this is averaged over each OD pair, or K vantage points, and is shown in dark blue. For the paired estimator, this is averaged over each level across all the OD pairs and is indicated in light blue. The rightmost plot shows the worst case absolute error, or the minimum deviation from ground truth across all estimates yielded by a single OD pair or level. Notably, the worst case error is only about twice the average error. The relative improvement in the robust estimator in the worst case compared to average is consistent with its robust character. By averaging over all the levels, we are able to mitigate noise due to MSP failure. This is a real-world example highlighting the limitations of the unpaired estimator and the robustness of the paired estimator. Here, in this case, MSP holds at the highest level we see for the RTT signal. So the raw RTT signal in this figure is shown in red, and the ground truth dataset is shown in black. If we are to simply take the lowest level of the red signal as the minimum, our estimate would be moving away from the true minimum. This shows the risk inherent to assuming that the lowest level corresponds most closely with ground truth. What these examples make clear is that the accuracy of any estimator is ultimately bounded by whether MSP holds. And because MSP is rarely guaranteed, this has important implications for what kinds of fine-grained measurements we can hope to obtain. In ground truth data, where MSP holds, we found that estimates of the mean and minimum are typically so close that they are practically indistinguishable, such that latency variation over these links would lie under measurement uncertainty. However, in the case where MSP does not hold, then the difference between the true minimum and the mean RTT would be negligible compared to the spread of levels observed. In other words, any measure of standard deviation would be heavily polluted by noise from MSP failure, each of the levels due to MSP failure correspond to a different underlying path. Unless we can hope to solve MSP, it is pointless to imagine we can split the levels to assess variance or anything finer grained with data of this type. In summary, this work gives us a solid foundation for vantage point identification and calculating minimum RTT in the submarine cable network, and it highlights the limitations inherent to capturing fine-grained dynamic properties using active measurement. Please direct any questions to my email or reach out to me in the Discord channel and I'll be happy to connect.